All right. Hi. So we transition to lecture series number 6, which is data transformation techniques. You probably immediately notice one minor change to our lecture series, and that's the lecture series number. So previous versions of I think it should be lecture series number 4 had the data transformation component embedded within there. So that lecture series was tagged as data preprocessing and transformation. I just thought it would be helpful if we just factored out that particular component and just have a separate file. I think things will make a lot more sense that way. So you want to make sure that you download the most recent versions of lecture series number 4, right? And that's including the Jupyter notebooks. And in fact, for all files, what you notice is that you are constantly getting notifications via Google Classroom. You want to make sure that every time you get a notification, you download most recent versions of the documents. It's the only way these things will make sense. Like I said, same applies for the Jupyter notebooks as well. You want to make sure that you download the most recent version, not just the slides, right? Great. Okay. So, but before we start, I just thought just a few announcements here, and I'm not really sure when exactly you are going to watch this screencast, but if it happens to be before the deadline for some of these things, it's important to talk about these things. First off, a reminder that course management for CSC 5741 has moved to Google Classroom. Please accept the invitation. We still have maybe 3 or 4 people that have not yet done this. Please do this. And I hope I'm recording. I am. Right. The other thing is paper reading summary assignment number 2 is due on June 3rd. That's Wednesday. So you want to make sure you quickly read through the paper, comprehensively read through the paper actually, and then come up with a summary before Wednesday, right? And then on Tuesday, we have an academic talk by Zola Mahlaza. Zola is finalizing his PhD. So you probably want to attend this talk because in comparison to previous talks, this is going to be heavily theoretical. And as people say, it's going to be computer science-y, right? So you probably want to attend this. Right, so the lecture series is going to be segmented as follows. So it's split up into 2 parts. The first part is essentially just going to be a walkthrough of the basic concepts associated with data transformation, the theory around some data transformation techniques that we are going to place emphasis on. And then part 2 is essentially just going to be a walkthrough of some of the examples of how we go about transforming data. All right. I'm sorry about the noise. I have no idea what's going on outside, but people are screaming, probably a party or something. Right. So this is just an outline of the lecture series itself. It's going to be a relatively short lecture series, and I guess most of the unfamiliar content we're going to talk about is to do with transformation of textual content. Okay. So just to recap, we are still on phase number 3 of the CRISP DM model. So we're still discussing data preparation. We have, however, got into a stage where we know exactly what happens when we go through a so-called data selection process, how we clean data, right, and how we pre-process it. So how do we deduplicate? How do we handle null entries? When it comes to text, what sort of operations do we perform? So stop weight removal, stemming, techniques such as, and we didn't discuss lemmatization, but there's lemmatization as well. So these are all things to think about as whenever we're talking about preprocessing, and specifically for some operations, text preprocessing, right? We also had a lengthy discussion centered around how we go about deriving attributes, scaling of attributes, and also integration and merging of disparate data sets. All right, so to wrap up, we're going to wrap up the data preparation phase by having a discussion of data transformation, essentially. But to just set the stage for this so-called data transformation process, a reminder that we need to transform this data for precisely the same reason that we typically need to convert input data given to a machine in a form that it's able to understand, right? The reason we do this is because there's usually two different parties or stakeholders involved in this whole data consumption process, right? So when it comes to a typical computer, human beings understand data sources such as images and text, for instance, but a computer doesn't understand what this is. It doesn't understand what this is. So we typically have to convert all these different data types into a form that a computer is able to understand, right? And it's typically so-called ones and zeros, essentially, right? So this is computer architecture, computer systems 101 here. Similar to that, we typically need, before we can actually apply before we can make use of these estimators, before we can feed data to the estimators, the data that we need to feed, the input data or input features that we feed to the estimators need to be converted into a form that the estimators understand. Right, so when we're working with text, these estimators we're going to be working with, or estimators, or algorithms, whatever you want to call them, that we work with will not understand this. Right, so all these different data types have to be converted into a form that the estimator is going to understand. Now, a good way of trying to gain a better sense of how the transformation takes place is to remind ourselves of the different data attribute types that we discussed, I believe, in lecture series number 2, if I'm not mistaken. Right, we had a lengthy chat about, and in fact, our discussion was centered around so-called Stevens proposed scales, right, the topologies associated with these data types. We focused our discussion on so-called continuous data or numeric data types. We also looked at categorical data types, right, and of primary importance when we discussed categorical data types was this distinction between so-called nominal attributes and ordinal attributes. And so when you're dealing with categorical data types, you can either have two forms. So it's either you're dealing with unordered categories of data or ordered categories of data, right? So nominal attributes would be unordered categories, so male or female. Ordinal data types would be ordered data attributes. So there's a natural order associated with attributes, and it's typically associated with things that we see in surveys or questionnaires, Likert scales, for instance. To what extent do you agree with this? Highly agree, or agree, strongly agree, or something, right? There's a natural order associated with those different labels or scales, right? Another example, I guess, is if we were to classify, let's say, developers, for instance, right? Junior developer, senior developer, could be team lead or something, could be manager, right? There's a natural order there, right? Okay, but besides those data attributes that we discussed, just thought it would be important to make mention of the fact that there are in fact other data types that we get to work with whenever we are implementing or making use of these estimators. So should keep at the back of our minds that there are also different types of data attributes, and specifically we're making reference to things like sound, text, video content, images, right? I think it's something to think about here. But fundamentally, all these different data attributes have to be converted into a form that a computer is able to understand. Okay? Again, we need to do that because fundamentally these estimators would typically expect that we provide the input features in the form of numbers, not text or not raw images, but numbers. And so really, fundamentally, this whole data transformation process is essentially nothing more than a conversion process that takes data in this raw form, right? A form that human beings are able to understand, into a numeric form that these estimators are expecting or be able to interpret. So our focus really in this lecture series is just going to be on how to transform nominal attributes ordinal attributes, and text, right? We won't really look at interval or numeric attributes because they're already numbers, right? Great. So start off with nominal attributes, right? So again, typically the distinction between nominal and ordinal attributes is such that with nominal attributes, there's really no order associated with the different labels or categories, right? And so typically these data attributes are transformed using so-called one-hot encoding, right? So it's essentially a technique that binarizes the different labels or categories that you'd be working with, right? And the idea behind binarizing is you want to use a flag that is going to distinguish one category from the others, right? So if you look at the screenshot here, you notice that these images have so the entries that are highlighted in red here have markers that signal the fact that those particular record entries are associated with that description, right? So essentially, one-hot encoding will transform a label into a transposed format that allows you to use a flag to signal what sort of label you are associating to that particular observation, right? It's a very trivial process, really. And the reason why you want to do this is that the only other way that you'd convert, the only other ways that you'd actually end up converting these labels to numbers is, one, by the simplest form actually is to associate numbers to these different labels, right? So you could decide to say, okay, so I have English, missing data, civic education, and maths. What I'll do is I'll associate 1 to English, 2 to missing data, 3 to civic education, and 4 to mathematics. The problem with that approach, though, for categorical data is that you'd be implicitly signaling to the estimator that there's some sort of significance associated with the different labels, right? So the estimator might assume that civic education being assigned the number 3 means that civic education is greater than English. I don't know if that makes sense, right? So to avoid that, you actually use this sort of mechanism or technique, right? One-hot encoding. I guess another technique would be to say, okay, fine, fair enough. You associate numbers, let's say natural numbers, to these different labels, but then perhaps, so just to give you an example, you could say you're going to decide to associate English, missing data, civic education, and maths. You could choose to say you're going to associate numbers with these numbers to these different labels, but not just the numbers. You associate the numbers, after which you could perhaps convert these particular numbers into their binary equivalents, right? So you could say you're going to convert 1 to binary is just 1, 2. I hope that should be 2. 2 is 1 0. Sorry. I need to revise my hexadecimal to binary conversion, my knowledge of conversion from different number bases here. Right. So what you could decide to do is you could say, okay, fine, I will associate these things with binary numbers like so, but still the estimator will still assume that there's some sort of importance associated with this sort of order, which is why you want to use one-hot encoding, which is why one-hot encoding is actually used to transform nominal attributes into a numeric form that estimators will be able to understand. And you notice that once you transform the nominal attributes into a numeric form using one-hot encoding, the pattern is the same, right? The only distinguishing part to this pattern is where this flag, which is the one in this case, is going to be placed. So if a flag appears under art and design, then you know that that particular observation is associated with that particular that particular value of the attribute, right? So, which is why you're saying the pattern of ones and zeros will actually determine which label is going to be associated with the observation. So ordinal attributes are different, though. Remember that the one distinguishing characteristic of ordinal attributes when compared with nominal attributes is the fact that there's usually a natural order or an implicit order associated with the labels, right? And so for you to encode this into a numeric form that a computer will be able to understand, you could just assign numbers to the labels, right? But you assign the numbers in such a way that they explicitly signal exactly how they compare to the other labels, right? So if you look at this example, for instance, what we're saying is that because no experience is essentially similar to zero, this is the starting point. What we're saying is that we're associating 1 to a person who has zero experience working with computers. Could just as well have been 0. It doesn't matter. We could have just as well have started from 0 all the way to, in this case, 3, but we just decided to start with 1. These are weightings we're associating to the labels essentially, and the weightings will signal the relative importance of the label itself, right? So no experience is associated with 1, less than 1 year is associated with 2, 1 to 2 years is associated with 3, and then more than 5 years is associated with 4. Now, what you immediately realize here is that this particular example assumes that the gap between these different labels is the same. But of course, there are certain instances where the gap might not really be the same, right? So if you, let's see here, if we were to, and this is a good example actually, if we were working on a problem that would require for us to, and I hope I'll be able to find this. There we go. If we're working on a problem that would require us to, let's say, cluster human beings in Zambia based on their earning potential, right? Their tax bands, you probably immediately realize that the gap between the different tax brackets in Zambia, right? These tax brackets that we normally work with, pay tax brackets, they're not the same, they're different, right? So the gap between the first band to the second band when compared with the third band to the last band is completely different. So the weightings that you'd associate to a problem such as this would be completely different, right? So something to put at the back of our minds. Yeah, and really the decision on what sort of weighting to associate to the labels is dependent on the domain itself. You'd obviously have to be more knowledgeable about the domain. If you're not, then you'd have to consult an expert who'll be able to explain to you what sort of weightings you'd have to associate to the labels. But the key thing here is the way that you transform ordinal attributes into a numeric form that the estimators are going to be able to interpret is by just assigning weightings to the labels. All right, and then there's a transformation of textual content, right? Hopefully this makes sense here. Just to quickly transition to how we go about transforming text. Well, it turns out really that there are quite a number of, it turns out that there are a number of techniques that are used to transform textual content into a numeric form that the computer will be able to understand, right? Now, our conversation, or at least our discussion in this course, is just going to be restricted to a so-called term frequency approach, or count vectorizer, if you're looking at it from the perspective of scikit-learn, and then the term frequency versus document frequency approach, right? So we're not really going to look at these other types of so-called word embeddings, right? I would like to think you're going to discuss these in the discussion that you're going to have with Dr. Piri. I'm not sure what that course is called, but it has to do with artificial intelligence or something. You should be able to, not you should be able to, you will actually discuss the different types of word embeddings, especially the ones that are more popularly used when taking deep learning approaches, for instance. But fundamentally, really, these weight embeddings can be clustered into frequency-based embeddings and prediction-based embeddings, right? We are mostly going to focus our attention on frequency-based embeddings. These are classic approaches that have been used for decades now, right? So we're going to restrict our conversation to temp frequencies and TF-IDF essentially. But just to mention that there are other approaches. So classic prediction-based embedding approaches will include, I think, techniques such as co-occurrence matrix, for instance, and the so-called continuous bag of weights, right? You probably want to look up these things just so you are familiar with how they are taken advantage of, essentially. But fundamentally, the goal is to, irrespective of the sort of approach you take, the goal is to move from this sort of approach here, where you have textual content, into this approach here, right? So typically, text will be converted to numeric form by coming up with or deriving some sort of weight vector, right? So the image here is representative of so-called temp frequency, and the one below is associated with the TF-IDF, right? And we get to discuss this too shortly. But before we start our discussion, a couple of, I guess this is IR 101. It's a revision of our information retrieval course we did at undergrad. A couple of key terminologies that are going to be helpful as we discuss these two techniques here. Whenever we make mention of the word corpus, we're essentially making reference to a collection of documents associated to this problem domain you're working within, right? So if we were working with open-ended text associated with the motivation that the students cited as having influenced their decision to do this course, then all the open-ended text submitted by the students would form the corpus, right? So essentially, the entire data frame associated with major program motivation would form the corpus. This would be a collection of all the different documents. The document itself would be the individual entries associated with the different observations. Oh shit! So I'm sorry about this. This red bounding box here, it cut off the R's. It matters. I just thought I'd mention it. I wonder why it happened. Anyways, so the individual documents within the corpus would actually, the individual entries within the corpus would form documents, right? So this is an example of a document, right? So this piece of text here is a document. And then finally, whenever we make mention of the word term or token, we'll probably use these interchangeably, we are essentially making reference to the individual words. In this case, we're saying words because we've segmented the document down to words, right? So the individual word associated with each document, right? So using this document as an example, the terms associated with these documents would be the individual words, right? And you notice here we are clustering or separating the words using a space, right? So essentially, this document has a total of 1, 2, 3, 4, 5, 6 terms. Great. All right, so essentially the starting point whenever you want to transform text into numeric form is you need to tokenize the corpus. Right now, the tokenization process essentially involves you splitting up for each document. You split up each document into its constituent words or terms, right? So tokenizing means converting a document from this format into a format such as this, right? And you notice here that again, using our same example of the corpus here, we've tokenized all the different documents here, document 1, 2, 3, all the way up to 14 in this case, into constituent terms. So this process is essentially what's called tokenization. Now, there are obviously a couple of strategies that can be used to tokenize a document. You don't necessarily have to segment it this way. It essentially depends on the type of corpus that you're working with. If you think of classic example here would be the way search engines work, right? If you think about it, it's entirely possible that because the document associated with a typical search document, whenever you're talking about I guess it's CSC 741, when you search for something on the web, essentially, the documents, the word document in this case would relate to one of these search one of these results here, right? So when you look at this SRP here, search result page, each one of these results will represent a document, right? So if you think about this, I guess what I'm trying to say here, or what we're trying to say, is that the strategy that you use to tokenize a document is dependent on the type of problem that you're working on, and I guess the relative size of these documents, right? In certain instances, perhaps if you're working with relatively long passages, like for instance, if you say you are working with a corpus of yes, here we go again, electronic theses and dissertations, for instance, perhaps you might choose to tokenize or to segment those documents by using sentences, right? And I'm just reaching here, but I'm just saying that the strategy to use to tokenize the document is dependent on the problem, right? And also, talking about strategy here is how you get to construct this vector as well, right? In certain instances, the simplest way is just to count the number of occurrences of a particular word in a document. So given oh shoot, given this sort of corpus, for each document you just count the number of times want appears in there, the number of times acquire appears in there, the number of times this word appears in there, and then you take note of those numbers, right? That's probably one of the simplest ways of creating this vector, right? But there are other sophisticated ways. We'll soon notice this now. We'll soon learn. All right, so here's to hoping this whole tokenization thing makes sense, right? You're just breaking up the document into its constituent terms, right? And those terms will be called corpus, essentially. And speaking of tokenization, what you soon realize once we use classes such as count vectorizer and TF-IDF vectorizer here is that in certain instances, you don't really tokenize these words by just looking at the terms themselves, but you can further use advanced techniques where you get to you get to take into account words that follow each other, right? So I'm not sure if I'm making sense here, but okay, maybe an example would probably work best here. Count vectorizer. I don't know if the thing will work here, but yeah, probably not actually. Okay, probably not. Anyway, so there are certain instances, maybe this will work actually. Confused here. So the simplest way of tokenizing a word is, for instance, if you had the University of Zambia is one of the 70 institutions of higher learning. You soon realize that once we use classes such as count vectorizer, TF-IDF vectorizer, that you feed it or you specify parameters that will determine what sort of n-gram you want to associate to the vectorizer itself. So you realize that using this particular document, if I were to actually see this sentence as a document here, you realize that if you segment this based on the individual tokens, the meaning is somewhat lost, right? Because what you end up with here is a situation where you're saying there is a separate token, university separate token, but you realize that University of Zambia signals something. It has a certain meaning. In fact, their university has a certain meaning. Now, granted, once we remove stopwords and the like, this won't be there, but you realize that University of Zambia has some sort of intrinsic meaning, right? And which is why it becomes useful for you to take into account things like bigrams and trigrams, for instance, right? Or unigrams if you want. And really, very soon you gain an appreciation for why all of this is important, because it turns out that all these different techniques, how you choose to segment or to tokenize these particular documents, has an influence on the overall accuracy of the models that you get to implement, right? What we've noticed working with a few projects that we've worked on is trigrams usually work best, really. Bigrams and trigrams. It's usually the case. And we'll probably have an example. I hope we have an example in the Jupyter Notebook about this. Okay. Right. So essentially, really, again, just to reiterate, to emphasize this whole notion of why we are wanting to go through the painful process of tokenizing a document, splitting it up into its constituent terms or words, right? Remember, like we said before, that computers are generally not good at processing text, but they work well with numbers. So the reason we are tokenizing our corpus is so we get to a stage where we can associate numbers to the individual words or tokens, right? And really, once you go through a process of tokenizing a document, each document can then be thought of as being a bag of words, right? So it's essentially composed of terms with associated frequencies, essentially, right? So it's just an example again here. Similar example is what we have here. You notice that this is a two-dimensional vector where the first, it's a two-dimensional vector where my goodness, sorry about that. So it's a two-dimensional vector where you notice that this would be, it's not highlighting. I wonder why. That's unfortunate. Oh, I see. It's a picture. That's why. Okay, that's fine. Freehand maybe. So it's a two-dimensional vector where, if you notice, this part here would be document number 1, right? I don't know if people can see that. And then, so this marks the start of document number 1. And then document number 1 will end somewhere here, right? Document number 2, you notice, I never use this freehand tool. I don't use it a lot. So, but anyway, essentially, you notice that it's a two-dimensional matrix where each document is composed of the tokens associated with it, or the terms, right? Here marks the beginning of yet another document all the way up to here. And you notice that this is a relatively smaller document. It only has 4 terms here when compared with the first one there, right? So, right, so this is essentially what you go through. And really, the goal, again, of tokenization, coming up with this so-called bag of words model, is so you get to a stage where you can then associate numbers to the different tokens or terms associated with your document. Now, if you look at the term document frequency approach here, essentially what you have is a vector, right, which is representative of the terms contained in each of the individual documents of the corpus with their associated frequencies. So you notice that document 0 here document 0 has wonder why this is not working. Anyway, document 0 here will have I don't know if we can see here, but maybe this would be better. Document 0 here has, of course this is not represented, but the part that we can see here for the document is a relatively long vector, by the way. It's a huge vector, and there's probably words here that have slightly more numbers associated with them. But key thing here is that you notice that where you have numbers, whenever you have a 0 alongside the column label, it signals that that particular term does not exist in the document, right? So we can clearly see here that this word here, the stemmed version of always here, exists in document number 1, right? The word applique, which is perhaps applicable application, I don't know, appears in document number 3, right? The word always appears again in document number 5, right? Now, this is a horrible example here, but essentially you could have a situation where a particular document might have multiple occurrences of a particular word. So it's just by sheer coincidence here that these terms all have 1 associated with them. But maybe if we can go to the notebook, maybe we'll be able to find, I hope we do, we'll be able to find a classic example where you have a number other than 1 associated with the, my goodness, number other than 1 associated with the, perfect. So if you look at, and again, it's 1 and 2 here, but there's probably other words that appear multiple times here. If you look at the word Zambia, and incidentally also Zambia should have been stemmed, but because of the way the stemmer works, Zambia should have been Zambian should have been stemmed here. Wondering why they didn't get stemmed. Have to modify the Porter stemmer object that we're using, or class that we're using. Okay, so you notice here that for document number 4, for instance, Zambia appears 2 times, right? And in fact, if we were to, and again, I think we are reaching here, but if we were to kind of like check this for more occurrences of words, hopefully, probably not, but maybe if we tell it, perhaps, trying to see if we can find words that appear, doesn't look like it. Okay, that's fine. I guess it's a yet another horrible example, I guess. 40. Yeah, you see there are 2's here. So document number 28 here has the word also appearing 2 times, right? I want to mess up the notebook aesthetics here, so I'll change it back to 12. All right, so essentially the way the term document frequency approach, or the term frequency approach, works is you associate frequencies, so number of occurrences of each particular word per document, right? And this is a commonly used technique in information retrieval, obviously, right? Term frequencies. Great, but so the other approach that we said we were going to discuss here is so-called TF-IDF approach, where you, as opposed to checking for or assessing the relative importance of the word in that particular document, what you do is you go through a systematic approach, and it's a mathematical approach really, of trying to quantify the relative importance of the word when compared to the entire corpus, right? What we are looking at here is the importance of the word per document. What we're looking at here is its relative importance within the corpus, right? And it turns out really that it's usually a better way of trying to assess or associate numbers to words when you're working in a particular domain. Although there's a bit of an exception there. We've actually worked on problems where count vectorizer performs much better than TF-IDF vectorizer, right? So it's usually contextual, but in most instances the TF-IDF vectorizer works quite well. it results in better performance essentially. And that coupled with tweaking of other hyperparameters essentially. All right. So if you are, in case you are interested in trying to get an appreciation of the math behind TF-IDF, it turns out that you can actually compute TF-IDF by taking into account the temp frequency, right? So you take into account the temp frequency and the inverse document frequency essentially, right? And in fact, you can actually compute the temp frequencies by hand, right? Even though when you're working with packages like scikit-learn, obviously, there are classes that will do these things for you, right? But essentially, this is essentially what you do is you're working with TF-IDF. TF-IDF is computed by taking into account the temp frequency and the inverse document frequency, right? And in each instances, you notice it takes in the word or the term here, right? So the formula would be like so here. This is supposed to be TF-IDF. It's not minus, by the way. TF-IDF is equal to the temp frequency multiplied by the inverse document frequency. The temp frequency is nothing more than the number of occurrence of a particular word in that document, right? And by the way, this TF-IDF is computed for each word in each document, right? So the word always, the TF-IDF value for the word always would have to be computed for document 0. You notice it's 0 here. The TF-IDF for the term always in document 1 is 0.5, right? In document 5 is 0.56. In document 9 is 0.46, right? And the way that you compute these numbers is by just using this formula here. So the temp frequency for this document, like if you were looking at, let's look at document number 2 here. If you're computing the TF-IDF for always, you'd first of all have to compute the temp frequency, which is TF. So temp frequency for always in document 1 here, always in document 1 is 1, right? It's 1, and then you then compute the inverse document frequency for the word itself, right? And the formula for the inverse document frequency is you just get the log of total number of terms divided by the document frequency of the word itself, right? And get the log value. I think when I was coming up with this lecture slide, I took the liberty of preparing this nice Excel sheet. I will share this. I know it's stupid, but it will probably help you compute these to actually systematically go through this to try and understand exactly how this works. So this Excel sheet has formulas that would be used to compute these different components that you plug into the formula, different elements that you plug into the formula. All right, something else you want to think about here is really the differences that you notice when you use a temp frequency approach versus the temp frequency versus document frequency approach, right? You can immediately see here that the TF-IDF approach is usually more precise, right? A classic example here is the word always. If we were to take the temp frequency approach, you notice that the word always has the same temp frequency value for document 1 and document 5. I don't know if people can see this, but if you look at document 1 here and document 5, right, and in fact even document 9, they have the same value for the same temp frequency value, right? But you notice that if you use TF-IDF, notice that the values that you have are somewhat different, and this is what you want to aim for, right? You want to go for an approach that is going to be as close as possible in deriving a representation of this text into a form that a computer will be able to understand, right? But again, like as earlier mentioned, it's sometimes desirable to use count vectorizer as opposed to a TF-IDF vectorizer. All right, so I just thought I'll just wrap up the brief introduction to data transformation here by reminding us that when you take into account all the different phases associated with the CRISP DM, the phase that's associated with data preparation is actually cited as being the most involving, right? So this is what we're wrapping up here. And really, we had a discussion about how these different sources of information actually go to compile these sort of results, but just something to keep at the back of your mind. It turns out to be the most involving component, right? You want to make sure you get it right. All right, so on that note, just transition to the Jupyter Notebook. So I'll see you just now so that we can walk through a few examples on how to transform nominal values into numeric equivalent using one-hot encoding, ordinal values into numeric equivalent using, I guess, what you might call label encoding, and textual content into numeric using count vectorizer and TF-IDF factorizer. All right, thanks.